Okay, so today we will continue from last time with linear algebra. And this is phone. Yeah. Okay, great. So last time, just to recap, we saw fields and vector spaces over fields. So, I mean, this is part recap and part new material, I guess. We saw fields. And the point is, some of these fields can indeed be finite. So you don't need to have infinite fields. And you have a V is a vector space over a field. Now let's do it this way. Okay, so this is what we saw. We saw the definition of a field, the definition of a vector space over a field, and these were sort of similar, not very different in nature. Okay, so then what is next? So maybe I'll recap by reminding you a little bit about the field axioms and so on, and we will go a little more into a field. What is it? What certain properties of a field? Okay, so remember examples. So the first one, I said the real numbers and the complex numbers. So I'll remind you that R is a field. The set of complex numbers, and let me write this down: a plus bi. So I is the square root of -1. I should give myself some space. A, B in R. This is a field. So now let me just tell you it's a field in what sense? It's a field under the following operations. So addition is just, we know what it is. A plus bi plus C plus di is A plus C plus B plus D I. That is addition. Multiplication is slightly trickier. A plus bi times C plus di. So there is some real part, and then there is some imaginary part, and you all have seen this before probably, but let me just, if you haven't, formally define it for you. So real part is AC minus BD. Interestingly, this is not plus but a minus, and that comes from the fact that I times I is -1. So BI times DI is minus BD. Okay, and then this one is the remaining part is AD plus BC. Okay, and I hope all of this is visible. It seems to be. So these are the addition and multiplication. The 0 is just the zero added by identity is 0 plus 0i. The 1, the multiplicative identity is 1 plus 1i. Let me just put these. And the most interesting part, of course, is how do you define the reciprocal? That is the remaining part. So I need some space for that. The reciprocal is defined in the following way. You write down A, so I want 1 over A plus bi, right? So let's write that down. So let's make this is a bullet point, and 1 over A plus bi. And what does it mean to say this is non-zero? Well, the zero element is when both the real and the imaginary part are 0. So 1 over A plus bi being non-zero, either A or B is non-zero, or both are non-zero. Okay, so that's what it means. Now, what I do is, this is something you have seen in whatever. I mean, even if you haven't seen complex numbers, you have seen how to simplify this using sort of multiply and divide by the conjugate. And the reason why you say conjugate is this is also a square root. A plus B root minus 1. The conjugate is A minus B root minus 1. So you multiply and divide by the conjugate. And now remember, we have defined how to multiply things. So if you have A, B, and A and minus B, then this becomes A times minus B plus B times A. That is 0. So there is no I component in the denominator. And what is the this component? This is A plus B. sorry, and it becomes A times A minus B times minus B. So it becomes A squared plus B squared. So this becomes A minus BI divided by a real number, A squared plus B squared. So how do you write it as a new complex number? Well, remember, you have to write out the real part and then imaginary part. But now you can. It's A over A squared plus B squared and then minus BI over A squared plus B squared. So this is how you define these are the operations that you define. So maybe I should have said definition, 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 and so these are all definitions. Okay. Once you have these definitions, you have to prove or verify for yourself that these definitions satisfy the axioms of the field. They satisfy the field axioms, and that is why the complex numbers form a field. So why do they satisfy the axioms? So, okay, so that's I will. So for example, check that these satisfy these operations. This is fading out probably. That's fine. Satisfy. Check that these operations satisfy the field axioms. So how do you check that? Okay, so one way to check that is to go by scratch. So let's look at addition being commutative as an example, right? So for example, so if I take instead of A plus B di, addition being commutative, so plus is commutable. If I compute C plus di plus A plus bi, then what do I get? By the same definition, I get C plus A plus B plus bi. Now, why is this equal to this number? So, I want to check that if you add these complex numbers in this order, which is this, or you add them in the reverse order, which is this, you get the same answer. Why? Because you have to then check that the real parts are equal, A plus C and C plus A, and the imaginary parts are equal, B plus D and D plus B. But that is obvious if you assume that R is a field, because these are the sums of two real numbers. So of course they are equal. This number and this number are equal. And similarly, B plus D and D plus B are equal. Because addition is commutative in R. Okay, so that's going to be one of your homework problems, which is to say, find out when is A plus BI. Sorry, verify these things. Verify that the homework is to verify that C is a field using the fact that R is a field. Meaning under these operations, they satisfy the field axioms using that R is a field. That will be one of your problems in homework set 1. Okay, so that is one thing. Oh God, I forgot when I started. Let's say at 6:40. Fine. So, okay, so that is one thing. Now next, let's get to. So you are allowed to use this, which means you don't need to. So what I expect you to say is that addition is commutative just because over C because it's commutative over R. Okay, you don't need to write out all this thing. Similarly, you can say addition is associative over C because it's associative over R. But for multiplication, you actually have to verify things because here it's not just over R. These formulas are very strict. So when I say verify this thing, I basically mean verify the axioms that involve multiplication and the distributive law. For all of those, you have to verify that that works. Okay? So and you don't even need to. Okay. So when I say using that R as a field, you don't need to refer to it. You don't need to say this in your answer, but just use it. Remember that you are allowed to use it. where needed. Okay, so just use it wherever necessary. You don't need to say that, okay, because addition is commutative enough, therefore this happens. Yes, sir. Okay, so that is that. Let us now get to the next field. I told you about rational numbers. I'll just mention it because then I can just finish the examples. So again, when I said that Q is a field, I should have defined for you the operations. So here are the operations basically. For instance, P over Q plus R over S is defined to be what? Well, again, you know what to do. Q and S are non-zero integers. So Q times S is non-zero. And then the numerator becomes P times S plus Q times R. Okay? And similarly, P over Q inverse. Well, this inverse only makes sense when this number is non-zero. You already know Q is non-zero. It means P also is non-zero. And then the inverse definition is obviously Q over P, and so on and so forth. The multiplication is PR over QS, and so on and so forth. This is a field. Again, this involves verifying that the field axioms hold. And that involves basically using the field axioms for the integers. You need to know that addition in integers is commutative or commutative and associative. Multiplication of integers is commutative and associative. Distributive law holds over integers, and so on and so forth. Okay, so that's the kind of stuff you would need to verify to prove that Q is a field. I won't ask you to do it. Okay. So that is one thing. And then let me tell you the final example I want from for a field, which we sort of, I mentioned it yesterday in greater generality, but let's look at it specifically today. So remember that I told you that in any field, 0 and 1 are distinct elements, right? So that means that every single field has to have at least two elements, 0 and 1. So can there be a field with at least two elements, with exactly two elements? Get the smallest possible number. The answer is yes, and that is our final example, I think, for today. That's the field with two elements, 0 and 1. I can call it 0 and 1, I can call it X and Y. It doesn't matter what I call these elements. Just because I tell you that here is a set of two elements, which is a field, that doesn't make it a field. What makes it a field is when I give you the operations, the field operations. How do you define plus? How do you define times? What is the reciprocal? Right? Which is the 0 element, which is the 1 element. But hopefully I call these because this is going to be the 0 element and this one the 1 element. Right? But so let's see why. Now remember what I told you this was. This was supposed to be the integers when you, or the remainders possible when you divide numbers by 2. Well, there are only two types of numbers then. Those which leave a remainder of 0 and those which leave a remainder of 1. Those are what I will call 0 and 1. So that means I'm really talking about even and odd. And that's really what you should think of these, right? So now that's going to guide how I define my field operations. Well, if you add an even number and an even number, I get an even number. So I'm going to say 0 plus 0 is 0. If you add an odd number and an odd number, you still get an even number. So 1 plus 1 is also 0. So although we say 1 plus 1 is 2 in our usual number system, in the real line or in integers, here 1 plus 1 is 2 actually equals 0 because when you divide 2 by 2, the remainder is 0. Right? So the operations are as follows. So plus is defined to be as follows: 0 plus 0 equals 1 plus 1 equals 0. And 0 plus 1 equals obviously 1 plus 0 because it's commutative. That is fine. What about multiplication? The same way. Even times even is even. The only one that is not even is odd times odd. So 0 times 0 equals 0 times 1 equals 1 times 0 equals 0. And 1 times 1 equals 1. And this should also already tell you that 0 added to anything gives you back that same number. 0 plus 1 is 1. 0 plus 0 is 0. So 0 is the additive identity. 1 times anything is 1 times 0 is 0, 1 times 1 is 1. So 0 is the 0, 1 equals 1. So I mean, you know how to make sense of these statements. The additive identity is this 0. The multiplicative identity is this 1. What else do I need? I guess just the minuses. So well, that's clear from here. 1 plus 1 is 0, so 1 is minus 1. And 0 plus 0 is 0, so 0 is minus 0. So okay, that's another thing. So negatives are done. Finite the reciprocal. Well, 0 cannot be reciprocated, but 1 can. Because 1 inverse. Okay, and now you have to check that the distributive law holds, that addition is commutative. Well, that's here. And so on and so forth. Addition is associative, but you can check that. I mean, you can check that. So yeah. Okay. So that's what it is. So I think these are all the examples I wanted to give of number systems. But basically what we are doing here is modulo 2 arithmetic, or block arithmetic, right? Okay, so now the next question for your homework is, I think just like we showed last time, that the element 0 is unique. Right? If there are two 0 and 0 primes, then 0 plus 0 prime can be computed in two different ways. You get 0 equals 0 prime. The same things happen for, so this should be your homework. The same thing happens for 1 and so on. So these will be put up on the homework page, on the course website, don't worry. Okay, so we are going to show on in any field F. Okay, so we will show that, let's see, 1, the negative, and the reciprocal, for which A is non-zero, are unique. For all A, and for this one, of course, A must be non-zero. Okay, that's one question. Then you have many other things. You have something like this: 0 times anything, 0. 1 times anything is 1, of course, but minus 1. Minus 1 is the negative of 1. Times anything is minus A. Negative 1 square is 1. And lots of different such things. Oh, and here is a very useful result. Suppose I know that A times B is 0 in the field. Then this is if and only if either A equals 0 or B equals 0, and the OR is inclusive, so both can be 0. 0 times 0 is 0. But at least one of them has to be 0. If both A and B are non-zero, then A times B cannot be 0. Okay, so one implication clearly follows from here. The other implication is the converse implication is the problem, which is that if AB equal to 0, then why is either one of them, at least one of them, equal to 0? So that's another question for you guys to figure out. Okay, but this question is this particular fact is going to come in very handy just now when we further investigate a field. So now we are going to talk about something called the characteristic of a field. Okay, so definition. So let's say the field is F, the characteristic is called char F. The characteristic of the field is the smallest positive integer is the smallest positive integer. This is all legible, yes. N bigger than 0, such that if you take 1 plus 1 plus 1 plus 1 n times, then you get 0. Okay, it's the smallest positive integer, so that if you add 1 that many times, you get 0. Clearly, if you add 1 one time, you don't get 0 because the field axioms specifically say that 1 doesn't equal 0. But maybe when you add 1 two times, you get 0. In that case, the characteristic is 2. When you do division modulo 3, when you add 1 three times, you get 0, but not 2 times, not 1 time. So for z mod 3z, for f3, the characteristic is 3. Similarly, for fp, the characteristic is that prime number p. But does the characteristic always have to be such an integer? So here is where again, so there's this very nice chess channel that I sometimes see. And so let me pause the video here for a couple of seconds. Basically, when you can pause the video here and try to figure out the answer. And so if you figured out the answer, great. And if not, for those of you who just want to enjoy the show, the answer is no. Sometimes it is the case that you can keep adding 1 and never get to 0. In the most natural place possible, in the integers, in the rational numbers, right? If you take the field to be R or Q or C, complex numbers, then you can keep adding 1 as many times as you want, and you will keep getting bigger and bigger positive integers, never 0. So in the case that this will never get to 0, the field is said to have characteristic 0. Let me write that down. If no such n exists, n bigger than 0 exists, we say f has characteristic 0. This is the last time I think in the course that I will write the word characteristic. Oh, until we get to the characteristic polynomial of a matrix. But for now, this is it. After this, I will just say char f equals 0. Oops. Okay, so that's the characteristic is denoted by char. Okay, so the characteristic of the field is 0 if you can keep adding 1, 1, 1, 1, 1 and never get to 0. Okay, so now the point is, what are all the possible non-zero integers, positive integers, that can be characteristics of a field? Clearly, all the primes can be characteristics because fp, z dot pz has characteristic p. Okay, for example, let me give you examples. The characteristic of fp is p, which is a prime number bigger or equals 2. Characteristic of the real line, or the complex plane, or the rationals, all of these have characteristics 0. Okay, so these are characteristics. Fine. Let's say that here. Okay, great. Okay, so this is the characteristic of the field. And as I said, so let us first ask, we have all the primes are characteristics, 0 is a characteristic. Can anything else be a characteristic? Can I have 6 or 21 or 42 to be the characteristic of a field? So the answer is no, as our next result proves. So I'll prove 2 results right now. As I said, my point is to try to understand the structure of a field in slightly greater generality. So let's call this a proposition. So f is any given field. F is a field. So 2 statements. One is that the characteristic of f is either 0 or a prime integer, and the second is that f contains a unique smallest subfield. What does a unique smallest subfield mean? It means that if you get, so you have a field. The complex numbers is the field. It contains the real numbers, the real line as a subfield. Right? It's a subset which is a field under the same operations. You can't just choose different operations. The given operations in the field, this is a subfield, right? So, but the real line is not the smallest subfield inside the complex numbers, because the rational numbers sit inside the real line and they form a subfield. Now, is there a subfield even smaller than the rational numbers? That's the question. Which is the smallest subfield in the complex field? We've gone down from the complex to the real to the rational, but maybe there is something further sitting inside it. Let's check. Yeah. Okay. So, what does this smallest mean? Means, i.e., let's even call this something. Let's call it f prime. Okay, that's too big. Let me call it f min. Min stands for minimum, right? So, why do I not have it here? That means that if f contains E as a subfield, then E necessarily. Why? Okay, again, also I'm wasting a lot of space here. i.e., if f contains E as a subfield, then E has to further contain f min. So any subfield of the field f must contain this subfield f min. That's why it is the unique smallest subfield. How do you prove this? I think that's what I have to prove now. And I should point out, of course, a subfield itself. A subfield just means a subset that is closed under the field operations. Plus, minus, times, reciprocal, and containing 0 and 1. So it has to contain the additive identity, the multiplicative identity, and be closed under those for the field operations in the field f itself. That's what is called a subfield. So, yeah. Okay, so great. So now let us talk about, let's see the proof. Maybe I can write the proof. I can start proving it here. Part 1. Right, so suppose the characteristic is not 0. We have to prove that then it is a, so first of all, if it is not 0, then there is at least one positive integer, and in particular a smallest one, such that 1 plus 1 plus 1 is 0. Right? So suppose, but in short, in fact, let me even say that. Here. Let's say it is actually fine. Let's say non-zero. So it equals n. So some n. Equals some n. Okay. In fact, it can't be 1, because why cannot n be 1? Because as I said, 1 does not equal 0. So it has to be n bigger equals 2. Let's start with that. The claim is that n must be prime. Why? If n is not prime, then if n is composite, then n is a product of two different integers. Let's say n equals a times b. Now, as integers. Okay, so, well, if I add a times b many of these, that's the same as saying I add the number which is a times, multiplied by the number which is b times sum of b many ones, and that product is 0. Right? So let's say suppose n is a times b in integers or in the real line. Then what we just proved then is that 1 plus 1 plus 1 a many times 1 plus 1 plus 1 b many times. This is together equal by the distributive law. This is equal to 1 plus 1 plus 1 n many times, a d many times, right? So this product is 0, but this is 0 in f. And this is where we use the exercise that I have already erased. The last exercise there said that if, let's still call this a and b. But if a times b is 0 in f, then either a is 0 or b is 0. Oops, I should have said that. Suppose n is a times b. And that's fine. So if this is 0, then either a is 0 or b is 0, right? Let me just say this thing. Say n is a times b, and I want to prove that n is a prime. So I'm assuming I'm proving it by contradiction. Suppose n equals a times b with a and b both bigger equals 2. That's the way you prove that something is not prime, right? A number is composite if it can be written as a product of two numbers, both of which are bigger equals 2. Then a times b is 0 in the field. So either a is 0 or b is 0. But you see, if a and b are both bigger equals 2, then they are strictly less than n. Let me just write this much, because I will need it in a second. Implies a equals 0 in f or b equals 0 in f by the homework. By the homework question. The last homework question which I wrote down and of course erased a few minutes ago. So by that, if a product of two numbers is 0 in two scalars is 0 in the field, at least one of them is 0. But you see, a and b are both strictly smaller. So remember that the characteristic, which was n, was supposed to be the smallest number of ones that added to 0. These are strictly smaller number of ones. So they don't add up to 0. Neither of them adds up to 0. So this contradicts the minimality of n. How can these both, either of them be 0? The smallest was this one. That's a contradiction. Of n, which was the characteristic of the field. So that the contradiction means that the assumption we made, assume that n equals a times b with both of them bigger equals 2, that assumption must be false. And therefore n is not the product of two integers strictly bigger than 1, so n must be prime. That's the definition of a prime number. Right? It does not admit a product factorization into two numbers, both of which are 2 or more. Okay, so sometimes. That is part 1. Part 2, f contains a unique smallest subfield. That is slightly more, this is not very hard. That is slightly longer. Not harder really, but it's longer. So what did you do is the following. How do you find this subfield? Right? So if you have any subfield, E or F main or whatever, any subfield must contain the number 0 and must contain the number 1. So this much you know. Now it's closed under addition and taking negatives. So it must, if it contains 0 and 1, it contains 1, 1 plus 1, 1 plus 1 plus 1, and so on. All the way, as many times as you can. And then similarly, it contains negatives. So minus 1, minus 1, minus 1, minus 1, minus 1, and so on. So it contains all of those. Let's start with that set and see what we get in any field. Okay, so so I'll define Z. So normally I would just say the integers, but because I'm working in a general field, For example, I could be working in the field of two elements. Therefore, I can't call it the integers because the integers are an infinite set. And if I just start adding up 1, 1 plus 1, 1 plus 1, and so on, I will get F2 in the field of two elements. I'll get the full field, but I'll get a field of size 2. I won't get an infinite set of integers. So let's call it this non-fancy usual set, which is the set of elements 1, 1 plus 1, 1 plus 1 plus 1, dot, 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 together with 0, together with minus 1, minus of 1 plus 1, minus 1 plus 1 plus 1. So this is a subset of L. So here, so this is contained in the field. Okay. Just define this subset. Basically, it's the set of integers in the field. Okay, whatever that means. Now, okay. So now there are, I think, two possibilities. I should have said something else. And I'll do that later. It's called the prime subfield. Okay. So now two possibilities. As we just saw, characteristic is either 0 or a prime. So let's say the characteristic is prime. And this is part 2. So case 1, if the characteristic is a prime number, then what do you get? Well, when you start adding 1, 1 plus 1, 1 plus 1 plus 1, and so on, you will get all the prime number of elements, right? You'll get 1, so you start with 0, 1, 2, 3, p minus 1, and p which is 0. But then similarly, minus 1 is p minus 1, minus 2 is p minus 2. So all of this just gives you those p many elements. And then z equals fp. If the characteristic of the big field f is p, then z equals fp. I'm not saying that z equals that the field itself is fp. No, the field can be much bigger. The field can have p square elements or p cube elements. This set that I identified is equal to fp. That's all. It's a finite field sitting inside f. Okay, great. Now what do we do? This is case 1. Fine. And then in this case, I want to define q. Again, this just like the z was supposed to be rationals, integers, this q is supposed to denote the quotients, set of all possible fractions. Well, the point is, in the field of remainders mod p, all the quotients already exist because this is a field. So if you take ratios of things in the field, you still get itself. So define that to just be equal to fp again. Okay. This is the case of this is the case when the field f has characteristic positive. I'm going to do the same definition first for the characteristic being 0, and then I will work with not the field separately but with this q. Okay. So now if instead the characteristic is 0, and these are the only two cases by part 1. Right? The characteristic is either 0 or a prime. If the characteristic of my original field here is 0, then z is basically in bijection, or it's much more than that, with the integers, right? Because you will never repeat two elements. The point is, if 1 plus 1 equals 1 plus 1 plus 1 plus 1, then it's like saying 2 equals 4. So you can subtract and say 2 equals 0. But you'll never get to 0, and therefore you never repeat these numbers. I'm not proving that. But that's why it's really 1-to-1 bijection. This is 1, this is really 2, this is really 3, and so on. This is negative 1, this is really negative 2, and this is really negative 3. If the characteristic of your field is 0. Only that case. Okay? And then in this case, define. Again, this time the q will actually be like the rational numbers. And this is why, well, this is not why, but this is where you should recall I had asked you the description of the rational numbers. That's what we do here. Except I don't say p over q, because what is 1 over q? It is p times q reciprocal. That's what we write down. pq inverse such that p and q are in this z set. Now, this is not the fancy integer set, and q obviously is not 0. Define this to be my q. The claim in both cases is that Q is a field. And the claim is Q is exactly this smallest subfield. That is what we are going to prove. Okay, so why is Q of, so let me see, what do I want to prove? I will see. So, okay, in both cases, meaning it's a subfield of F itself. That is the first point. And the second point is that it will be the minimum one. So if E is any subfield, then E contains Q. That is part 2. Let's first prove this claim. Let's call it claim 1. So this is claim 1. Proof. So how do you prove that a subset of the field, this is clearly a subset of the field, right? How do you prove that a smaller set of elements inside a field itself forms a field under those operations? Right? So under the operations. Under the operations in F. How do you prove that? So to prove that, all you have to check is, so okay, is addition commutative? So suppose I take two elements from this field, Q, from this subset, A and B. Is A plus B equal to, or Q1 and Q2? Then is Q1 plus Q2 equal to Q2 plus Q1? It obviously is, right? Because these are elements in the bigger field. In the bigger field, the same operation says commutative. So of course it's commutative. Is multiplication associative in this field? Again, these elements are in the bigger field. Multiplication is associated there. So of course the answer is yes. So what is there to prove? Is there anything to prove? Again, let me pause the video for a couple of seconds. And so for those of you who found it on your own, great. For those of you who want to just enjoy the show, this is, I'll stop saying this after this class. But yeah, it's worthwhile thinking about it yourself. The point is, it's the proving the field axioms is not the point here. That will always happen because they lie inside the bigger field. What you have to prove is that the sum of two elements of Q itself lies in Q. You have to prove the closure of Q under those field operations. The inverse, the reciprocal, the negative. These things lie in Q whenever the element lies in Q. That's what one has to verify. Not that the addition is commutative or the addition is associative and so on. Those come for free. The closure of the set under those operations, the subset, is what doesn't come for free. So you can check this. So clearly, the claim is it's a subfield. This one is, so there's nothing to check here. So let me just say e.g. for in case B, let's say I have PQ inverse plus RS inverse, and then we know exactly what to do, right? Which is this is equal to what? It is this times QS inverse, and this is PS plus QR. And this is again why I wrote down that formula today, earlier today. How do you write down P divided by Q plus R divided by S? You write PS plus QR over QS. So that's what we did. And so etc. Or PQ inverse equals QP inverse if PQ not equals 0, and so on and so forth. So yes, indeed these things. So clearly this is an element of Q. Clearly this is an element of Q. So yes, taking reciprocals does not go outside the set Q, etc. So yeah, I leave the product for you. Okay, so that is the first thing. That yes, it's a subfield. And of course 0 and 1 belong to so that's why I wrote the etc. But if you want, you can write down PQ inverse times RS inverse, and then also you can write down 0 and 1 indeed belong to Z, which is a subset of Q. Why is Z a subset of Q? Because I can take little q here to be 1. So P times 1 inverse is just P. So for every P in Z, P equals P times 1 inverse, and therefore Z is a subset. Okay, so that's the first claim. Claim 2. What is the second claim? It is the fact that this Q is the minimal field. So if E is a subfield of F, then Q contains E. Why is that true? I'll just sort of write down a quick proof. Why is that true? Again, you can pause and think for yourselves, but basically it comes from here. Okay, so for those of you who just want to enjoy the show, what we do is the following, right? We say, well, first of all, because, okay, if E is a subfield, then 0 and 1 are clearly contained in E. Okay, but then because of 0 and 1, because E is now closed under addition and negatives, therefore all of these guys are contained in E. Because 1 is contained in E, E is closed under the field operation, so 1 plus 1 is contained in E, 1 plus 1 plus 1 is contained in E, and so on. Implies Z is contained in E. Okay, but again, E is a field. So it is closed under the quotienting operations as well, reciprocal and multiplication as well. This was just the addition part, this was the multiplication part, right? Multiplication and reciprocal. So because Z is contained in E, now I can take Q to be non-zero element of Z, that's in E. Therefore, Q inverse, the reciprocal is in E, E is a subfield. P is in E, so P times Q inverse is also in E because E is closed under multiplication and so on. And that is the end of the proof, right? So we have just shown that indeed this is a set of elements, either this one or this one is a set of elements, which is first of all a field, second of all a subfield of the original field, with those operations actually, and thirdly it is contained in every single subfield of F. So it is indeed the unique smallest subfield. And now here is where as I said, I'll give you the name, definition. So Q, which is equal to this F min or whatever, is called the prime subfield. Okay, that's the definition. Okay, so that is that. So in particular, we again have, so let me just summarize this part of it here. So therefore, as a corollary to this proposition, or this theorem, as a corollary, if the characteristic of the field is 0, let's say the characteristic of the field is a prime, F min, the prime subfield, is literally the field with P elements, which is Z mod Pz, Z mod Pz. If instead the characteristic of the field is 0, then F min is precisely this set. But as I said, this is really in bijection with its isomorphic as fields to the quotient field of Z, which is the rational numbers. So I mean, I'm saying equal to, but that it really is equal to that. You can identify what is a 1, well, the 1 is a 1, and therefore you know what is 2, you know what is 3, you know what is 4, and you will get all of them because the characteristic is 0. And then the -1, -2, -3, and then you can define 5 over 7. 5 times 7 inverse, meaning 1 plus 1 plus 1 5 times the reciprocal of 1 plus 1 plus 1 7 times. That is 5 over 7. So it really actually equals Q for every practical reason. Okay. The next, so here is an example of a field that can contain a smaller field, the field Q, right? Well, so now let me come to examples of vector spaces, I think. Yeah. Starting with this one. Maybe this is a nice time to switch colors. One is exactly the case that we have just now. Suppose I have a field, a bigger field F, and a smaller field E, where E can be equal to your prime subfield F min or not. You can decide. Okay, so say E is a subfield of F. Then F is a vector space over E. Every bigger field is a vector space over every smaller field. Okay. So F is an E vector space. This is in fact not just the first example, it's also a homework. Okay. So this is one example, and in fact this is an example that explains why the field of 16 elements does not contain the field of 8 elements. It also explains why the only sizes that finite fields can have are powers of a particular prime. And you can guess which prime. The prime in the prime subfield. Okay? So by the way, already this tells you something, right? It tells you that if the characteristic of the field is 0, then because the field contains the rational numbers, and the rational numbers are an infinite set, so the field itself has to be an infinite set. Well, already we knew that because the field contains sort of the integers, and the integers are an infinite set. But yes, so you cannot have a finite field with characteristic 0, because you have to keep adding 1 and sort of. Okay, think about it if you want, but yeah. So this is one example, okay, and you can verify things like that, right? So basically you are saying something like this: E times E prime times F equals E times E prime times F. Well, these are all obvious statements because this is all true in the field. In the field F, multiplication is associated, therefore this is true. And the rest of the things like this, the distributive law as a vector space and scalar multiplication is just the distributive law in F alone. And so, okay, so again, so you can just say such things that the scalar multiplication properties hold over in F over E because of the properties of multiplication and the distributive law in F alone. You can say such things if you want. But I would like you to just write these down and verify that you understand how to work with field axioms. Because again, this is sort of the last time, this week is the last time we'll explicitly talk about field axioms. Starting next week, we go to vector spaces, dimension, basis, Gaussian elimination, row operations, and so on. So we will never look at this again. So this is your first and only chance to sort of get some comfort, some familiarity with field operations and field axioms, which is why I'm asking you all these boring housekeeping jobs, like bookkeeping jobs, as homework problems. But that's the point. After this, you will never see this again in your life. So that's all. Okay. So E vector space, that's the first example. Okay, next. So in particular, let me remind you from last time. So from last time. And if I have a finite field Fp, so if I have a finite field, then the field must have size p power d. I won't give you the complete answer right now because we haven't yet defined vector space basis or dimension. So we don't have the tools to prove this in full rigor. But let me give you basically the proof modulo the small gap that remains, well, not the small gap, modulo one gap that remains to be addressed. And that is what we will address over the next few weeks. So for now, let me basically tell you the proof, but there's a small gap which I will mention. Okay, so why is this true? So why? So because, let me say proof in quotes because there is a gap. So first of all, what do you know? You know from the previous corollary or whatever, because the field is finite. Okay, so since I can even let me even tell you why. So let's see. Since f is finite, the sequence, the set, the sequence 1, 1 plus 1, 1 plus 1 plus 1. This is an infinite sequence. Here's a finite set. It always lies inside f. So necessarily, at least 2, in fact, infinitely many of these numbers must be equal to the same element inside f. This sequence must repeat. Somewhere. In other words, let's say somehow, so 1 plus 1 plus 1 m times equals 1 plus 1 plus 1 n times. But in that case, what do we know? It means that n minus m equals 0. If you add this n minus m times, then this is equal to 0. And this number n minus m is bigger than 0. But that means there is at least one positive integer such that you add 1 that many times you get 0. So the characteristic is finite. Which means it must be equal to some finite number p. But in that case, we know that if the characteristic is free, then f contains f min by corollary above. F contains f min, which is fp. Okay? And now I can apply this homework problem. If f contains fp, then f is a vector space over fp. And now comes the part that we haven't proved yet. Every vector space has a basis. And in this case, it has a finite basis. F has a finite basis. Let's call them V1, V2, Vd over Fp. What does that mean? So what does basis mean? I'll give you I'll tell you the definition, but we will formally define it and prove things later. Okay, so what does this mean? It means that every element of F, let's say V in F. So I'm thinking of F as a vector space, so I'm writing down vectors in F. These are all elements of F, by the way. Okay? Every is a unique linear combination, and unique combination over the subfield Fp. Unique Fp linear combination. Alpha 1 V1 plus alpha 2 V2 plus alpha d Vd, where all alpha I are in Fp. Okay? For every element of the bigger field, because it has this finite basis, it is a unique linear combination with coefficients from the smaller field of these vectors. So if you want to distinguish between scalars and vectors, let's underline the vectors. All the alphas are scalars. But that gives me a bijection of sets. Okay? This yields a bijection of sets from sort of alpha 1, alpha 2, alpha d in f to the d, fp to the d. Right? Because each element is in fp, so this thing is in the dx power of fp as a Cartesian product. 1-to-1 combination with v, which is the summation of alpha vi. And this is an element of the field f. This yields a bijection of sets between ft to the d and f, because every linear combination gives you every tuple here gives you a linear combination. Every linear combination is uniquely represented by tuples. That's the bijection. But then this implies that these two sets are in bijection, so they have the same number of elements. And what is the number of elements here? It's precisely p to the d. That answers the question, why? The only thing here, this is the big problem. I mean, not problem, this is the big unproved result. And that is the thing that we have to address. So that will take a few classes to develop carefully. First, I want to tell you about Gaussian elimination and row operations and solving linear systems. Once we deal with concrete matrices and so on, then we will get to the notion of abstract vector spaces, of dimension, of basis, of linear independence, of spanning sets, and so on. Once that is done, we will prove that statement there, that every finite field, every finite vector space over a finite field has a finite basis. Okay, but basically that's modulo that one big step, that one big leap for humanity, if you will. Modulo that thing, the rest of it is a complete proof. So I just need to tell you, I just need to prove this for you, which I will do in a month's time or something. Okay. So that answers the question of what I told you last time. We will see that every finite field has size a prime power. Well, this is roughly right. This is exactly right. Okay, so that was one example. So we started with one example of vector spaces, which was basically every field is a vector space over any subfield. Using that application, we just now this is the application. Using that, we just showed why every finite vector space has p power d many elements. But let me now go back to the examples of vector spaces. Right? So let's continue with examples of vector spaces. Over any field, there is a very simple vector space that one looks at, the field itself. As we just saw from the homework, f contains f, so f is a vector space over f. It's a trivial, tautological vector space. But there is an even simpler vector space than f itself. So let me start with that. And obviously, while I'm erasing, you don't need to pause the video, but you can try to think about what that even simpler vector space than the field itself can be. So more examples of vector spaces. One second. Okay, so one second. I just need to do one small thing. Okay, great. So I forget what I think. Example 1 was from fields. I forget what. Let me just start by calling it example 3. It may or may not be example 3, but whatever. Yeah. So so the simplest vector space over any field. So okay, last time I was mentioning about vector spaces over R. This is why this I want to do. Some of them will be essentially exactly the same thing, but over F. Others will be new. And this one was new because I didn't say it last time. The single element 0 is a vector space over real numbers, over any field. And the difference, you see, this is one difference between a field and a vector space. A field can never have one element. 0 not equals 1. But a vector space can have one element. Check. Right? So basically anything times 0. So what are the operations? 0 plus 0 equals 0. And minus 0 equals 0. And anything times 0, I guess alpha times 0 equals 0 for all alpha. Under these operations, the obvious operations, and if it is to be closed under addition, 0 plus 0 had better be 0. If it is to be closed under negatives, minus 0 should be 0, etc. etc. Okay, so that is one. Similarly, now last time as we saw, F itself is a F is a vector space. Vector space F. More generally, F to the D is a vector space over F for all D bigger equals 1. The operations on this are exactly what we said last time. You write down elements as A1, A2, A, A1, A2, AD transpose, and then you define and then you define this plus something else coordinate-wise, scalar multiplication coordinate-wise, and so on. So this is exactly what we did for Rn last time. This is the same thing. Similarly, again, another example that we saw last time. Take any set S and look at all functions from S to F. And again, define everything component-wise, or coordinate-wise, or entry-wise. Right? Okay, we just saw that F over a subfield is a vector space. The next one is interesting. The next one is going to be interesting. Let me do it where? Here. There, everywhere. The next two are interesting. Fine. My fingers. So. So remember I mentioned polynomials. The point is you have of course seen quadratic polynomials and how to solve them, cubic polynomials, maybe some Cardano's method and so on. But you can actually do this over any field, over any ring for that matter, but let's just say S is any set. Okay? Now here is my next example, polynomials. Okay, so this is denoted, let's say, I will just talk about polynomials in one variable. You can of course do polynomials in many variables. You will see this in your Algebra 1 class, those of you who are taking it. But yes, so polynomials, this is a vector space. So okay, let me write it. This is a collection of a0 plus a1x plus an x to the n. I need to write this bigger, I guess, for people to look at. This dot 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 plus a n x to the n, such that a is, first of all, n is bigger equals 0. And a0 and all ai belongs to x. Okay, and what is the component-wise addition and so on? So that we say that 0 is just 0, 1 is just 1, meaning 1 plus 0x plus 0x squared plus 0x cubed. Right? I can stop at n equals 0. So n equals 0 is just all scalars themselves. There are no x terms, n equals 0. This is like x to the 1, this is x to the 0. Right? 0 is 0, 1 is 1. Plus and minus are coordinate wise. Right? So like 5 plus 3x plus x is 5 plus 0 plus 3 plus 1x. So 5 plus 4x. You all know how polynomials work. Right? So I mean, I don't need to tell you that. That should be prerequisites for this course. That's a vector space over the field. It's much more than the vector space, but the fact that it's closed under multiplication is algebra 1. The fact that the monomials form a basis comes later. So for now, this is it. And then the final thing I want to do, and this is where we sort of stop with vector spaces. And the final thing I want to do, and it's roughly been an hour and 10, so we have 20 minutes more, is matrices. So now so this is the, what do I say? This is the switching point between vector spaces and matrix analysis or whatever. So let's give the last example, and very important one, which will occupy us for the next at least the next week, maybe the next 2 weeks, is matrices. Okay, so matrices. So what are matrices? Well, a matrix is just a rectangular array over the field F. Of scalars. I should have said somewhere that by scalars I just mean entries, elements of F. That's it. Yeah. So we write it down something like this: A equals A11, A12, A1n, A21, A22, A2n, Once you do enough LaTeX, so typing of mathematics, you know where to put the horizontal dots, the vertical dots, the diagonal dots. AM1, AM2, okay, this was slightly misaligned, AMN. Okay, so this is what one calls an M cross N matrix. This belongs to, where we write it, F to the M cross N. Okay, or sometimes one writes it as M by N here itself to denote the size of this matrix. So here each Aij line F. Okay, that is what it is. Okay, so so M and N are of course the dimension, the size of the matrix. M. So clearly you see how many rows are there. Well, the rows are given by the first index. 1, 1, 1, 2, 1n. This is the entries in the first row. 2, 1, 2, 2, 2n entries in the second row. There are m such rows. Similarly, 1, 1, 2, 1, n1. These are the entries in the first column. The second index talks about the column number. The first index talks about the row number. And so the general entry is Aij in the ith row and the jth column. This is. Yeah. Okay, so this is m rows and n columns. One thing, so why is it a vector space? This is a vector, so let me just quickly finish the fact about vector spaces. Of course, you can, you see how to add two matrices coordinate wise. So maybe I should say that. Okay. A plus B, then sort of C times A, scalar times the matrix, or negative A, which is just the same as minus 1 times A, are all defined. All are defined. All of them. So how do you define A plus B? So how do you define any matrix? You define any matrix by specifying its entries. So if I have a matrix A and I have a matrix B of both of the same size, of course, say m by n, and m by n again. Then I can add them up. The addition is valid. And how do I define this? I define it entry-wise. So what is the ijth entry of this thing? Well, it is the ijth entry of A plus the ijth entry of B. You just add them component-wise. Okay? All of them are component-wise. Similarly, C times A is C times Aij in every entry. Coordinate. I'll just say entry-wise. Or define entry-wise. Okay? But secondly, maybe I should have said this first, I don't know. The point is, what is f to the m by n, right? I mean, if I'm just going to define them entry by entry, it doesn't matter if I write down, like, if I write down A, B, C, D like this, or I write down A, B, C, D like this, or I write down A, B, C, D like this. They all mean the same exact thing. The addition is defined entry-wise. The scalar multiplication is defined entry-wise. Whether I stack them into a nice square shape, or a long column, or a long row, doesn't matter. The addition here between two such vectors is defined entry-wise, or between two row vectors. So what I'm saying is this f to the m cross n would really just be, so as a vector space, this is exactly the same. This vector space of all possible scalars ABCD is the same as this vector space of all possible scalars ABCD. It's exactly the same as f raised to m times n, either as a single long column or a single long row. And as this thing, f to the m cross n is isomorphic. We will explain about that later. F to the m. There is no difference between them as far as the field operations, vector space operations go. These are just the same thing, except instead of writing a long row or a long column, you stack them up into a nice number of smaller rows or smaller columns and call it a matrix. But whether you call it a matrix or a very long vector, the operations are all component-wise, so that doesn't change the structure. That's what I mean. Okay, so that's the last example of vector space. But now let's get in earnest at looking at matrices themselves. Okay, so more on matrices. Now that's the last we see of these vector spaces for now. We will of course see a lot more of vector spaces and dimension and so on, but later. Okay. So we have about 10 minutes, 12 minutes, so yeah. Oh God, after all that. Okay, fine, sorry. So more on matrices. So we already saw that the matrices form a vector space. Now let me look at some examples of matrices, right? And let's look at some more interesting things. So examples. The first one is when all the entries of the matrix are zero, right? In a vector space, there is always an additive identity. Well, what is that? The only one that can be is when you add it to any matrix, it doesn't change any entry. So every entry in that additive identity must be zero. So, for every size m by n, you have a zero matrix. Similarly, maybe I should call this example 0, and I should call this example 1. This I call the 1 matrix, all ones matrix. Right? So similarly, okay, I haven't defined matrix multiplication yet, but when I do, I will tell you that you can multiply matrices in certain cases. In that case, of course, you would want a multiplicative identity. Right? So all zeros matrix was the additive identity. Is it true that the all ones matrix is the identity for multiplication? We will see. If you haven't seen this before, then again, think about it. Try exploring whether this multiplied by some matrix, I haven't yet told you how to do that. Does it work as the multiplicative identity? We will find out. Okay. Here here is okay. So these are sort of all possible orders, rectangular matrices. So let me now define for you for such a matrix. I can define another rectangular matrix which switches the sizes. Number of rows becomes the number of columns. Number of columns becomes the number of rows. It's called the transpose. Okay. So 3. This is actually a definition. The transpose of a matrix A belongs to, let's even write down the entries. So I'll say it's Aij. So A is the matrix with entries given by Aij. Okay, this is defined to be. Oh no, let me first write down what it is denoted by, and then is A transpose belongs to F to the n cross n. As I said, the number of rows and columns switches defined as defined as, so A transpose is literally I just take all the entries and put them. So this was, I change all the rows to columns and columns to rows. So now this first row becomes the first column, A11, A12, A1n. The second row becomes the second column, A21, A22, A2n. And then the last row, AM1, AM2, AM. Okay, or in other words, this first row here was actually the first column here. The second row here was the second column there, and so on. Okay, so that is how you define the transpose. Okay, great. Now, so let me just make another definition. A matrix is said to be symmetric. Okay, first of all, the matrix is said to be symmetric if you change the transpose and you don't change anything. The matrix remains the same. Okay. Well, for that, first of all, the number of rows and number of columns are getting switched. If you are not going to change the matrix itself, then the size also cannot change. So the number of rows and number of columns must be equal. So when you have such a matrix, that matrix is said to be square. A in F to the M cross N is square if N equals N, or N equals N, and symmetric if A equals A transpose. That's what we mean. That's when we call it a symmetric matrix. Examples. For example, you have 1, -1, -1, 0. That's a symmetric matrix because if you switch the rows to columns, you see that you get the same thing. Basically, transpose, what it does is it reflects around this diagonal the entries, and you see the entries are the same. Okay, so here's another curious matrix, which is only made up of ones and zeros. Okay, that's a very nice looking matrix. It has ones on the main diagonal, zeros elsewhere. This has a name. Let's give it a name. I did not give it a name. Let's remind ourselves what this is called. This is called the identity matrix. And I'm sort of ruining the punchline here by telling you the name. But punchline basically is that yes, this was the additive identity. I asked if this was the multiplicative one. Well, it isn't. This one is the multiplicative identity. Okay, so we'll see that later. Okay, so that's another example. This is so transpose, square, symmetric, fine. This is not a definition. sorry, where was I here? I did square, symmetric, matrix. Okay. I'll just let me just stop in 1 more minute. This is long enough. So yeah. So if what if the I deleted the matrix, but what if the matrix is only one row, right? So if A belongs to F to the 1 cross n, then this is just like something like A11, A1n. Then this is called a row vector. And if A belongs to F to the m cross 1, which is just like, let's say A equals A11, A21, AM1, then A is a column. So clearly transpose takes row vectors to column vectors and column vectors to row vectors. Okay, so that's probably it for today. We will stop here with matrices and continue next time. So I have given you everything except I need to tell you start at matrix multiplication. Okay, so that's it for today. Stop the recording.